Hey guys, I hope everyone's doing well. My name is Tony Bichet, and I'm the Physics 2C SI. So what I'm doing today is I made kind of like a PowerPoint, and I put it on my iPad so I can like draw on it. So they're general topics, but I'm going to like go more in depth with what I write and whatnot. So just as like a primer, we're going to be talking about standing waves, but specifically um, waves in asymmetrical pipes. So pipes that are have one side that are closed and one side that's open. So like that, yeah, perfect. Move this. Okay, so and then we're going to be talking about we're going to just touch on electromagnetism, and then we're going to be talking about the double slit experiment. So with standing waves, this is definitely something you've seen before. Uh, the thing is, a lot of students don't understand why we have the certain equations. So I feel like if we get like a good grasp of why the equations are the way they are, then we'll better understand these type of problems. So what we see here is, well, first let me show this slide. This is the equation, okay, and you notice that. Let me change this color. There's a 4. We know that when there's two closed sides or two open sides, the equation is V over 2L. So why this change? Well, let's get into it. So as we can see here, there's a wave. Okay, that's bad. There's some sort of wave here, and let's try to characterize that according to the wavelength. So what is a wavelength? Um, it's the amount of time it takes a wave to go back to its starting position, right? So if we draw something like this, what am I doing? Okay, let's try this. So this is one wavelength. This is one whole wavelength. Now what we see here is what? We're really seeing this portion, okay? This portion, hopefully this isn't in the way. This portion is a fourth of this entire wavelength. So that's how we characterize wavelength based on the length. Now what we see here is a fourth of a wavelength, another fourth, and then one more fourth, which adds up to 3/4 of the full wavelength. Now, it's important to note that when we jump between um, the first and the second possible frequency, we're using odd numbers, so it's odd. Okay, so I want to bring your attention to this and this here and this here. These are two odd numbers. And the reason they have to be odd is because this open side has to end with an antinode. It can't have a node here. So it limits the type of confirmation the confirmations that could possibly be. Um, so hopefully that kind of like helps you understand why they're like that. And then if we look at the closed um, examples, this is the first possible, the first frequency. The first frequency looks like this, correct? This is half a wavelength. That's why the equation is based off of 2L. Okay, so let's go on. And yeah, these are important equations to remember, especially this one. This is gonna come up through through so many topics. It'll be like intertwined with so many different things. This is definitely something to keep in the back of your mind. Know this equation like the back of your hand. Super important. So let's get into electromagnetic waves. But the thing to keep in mind is that for electromagnetic waves, the electric and the magnetic fields are perpendicular to each other. Okay, so you can see here, there forms a 90 here. We can see that there is a 90-degree angle between them, so they're perpendicular. On top of that, both fields, this field and this field, they are perpendicular to the direction of the motion. So this is going to help you understand which direction the electromagnetic wave is moving, and we can understand these through polarizing filters. And so polarizing filters allow a certain type of orientation of a wave to come. So and these are used in picture in cameras, but this is important because I'm sure you guys remember the right hand rule. This is related to it. When you find the cross product of two vectors, a third vector is going to emerge, and this is basically what the right hand rule helps you understand. So yeah, electromagnetic waves. Some important things to note for the equations regarding electromagnetic waves. The speed is always the speed of light. So definitely remember this. 3.0 times 10 to the 8th meters per second. So we're talking about velocity. So this is velocity. It's important to note that because this has direction, so it's not just a speed. When we use it with this equation, this is a vector. There is an orientation in mind, or a direction in mind rather. So this is another important equation that has to do with the energy in a system. So this is energy, and definitely remember this. So I'm not sure if this is 2B or 2C, but when you had to learn about the what was it called? I think it's the work equation. Yeah, the work equation. But the kinetic energy of a valence electron that kind of comes off of a solid metal is going to be this energy minus the work force of the metal itself. So this is super important. So I want you to notice this frequency right here, this frequency. So if we were trying to find the energy of a wave and we only had certain characteristics, so this is the Planck constant, by the way. This is Planck's constant, and this is always given. I don't know it off the top of my head, but definitely something that you should know. I should know it too. So yeah, the frequency, we can substitute this with this equation up here. So this is V over L. And if we're talking about electromagnetic waves, this is going to be C over L, because this is 3 times 10 to the 8th. Okay. So last, but definitely not least, the double slit experiment. So this is Young's experiment to understand light diffraction. The thing to keep in mind is that the length, and the length refers to the distance between this, like the slits, and the screen. So this is L. This definitely has to be way bigger than this distance right here. This. So 2, 1. 1 has to be way bigger than 2. Okay, and this is definitely gonna happen because usually these are like millimeters apart. These are in a span of okay, these are in a span of meters. So Light from the two slits have the same phase constant. This is something important to remember when we're trying to talk about the total phase. This is definitely the sum. So waves can be constructive or destructive based on two things: the path length or the difference in phase constant. This is coming out of the same source, so there is no difference in phase constant. This is zero, but there is a difference in the path length, the path length, and we're going to talk about that next. And then here we see it produces both constructive and destructive wave patterns. So we see constructive, destructive. This is going to be the most intense. And then there is going to gradually decline in intensity as we go up and as we go down. So I think the light intensity will look something like this, if I'm not mistaken. Hold on, let me make sure I'm doing this right. So you've probably seen graphs that look like that. And you see this light intensity is decreasing. Okay. What else is important here? I think that's good. So this is definitely something to keep in mind. I wouldn't say it's necessarily important to kind of like know how to derive this, but just understand this. This is the most important thing to know, that this path length difference, this difference here, through some like trigonometric manipulations, we figured out this is d, which is the distance between the two slits, and sine of the angle. The angle changes based on where you are on the plane. So so let's say this is the slit. So the slit is usually really small. These are the two slits right here. This is obviously going to be, this is the middle right here. This is going to be a much greater angle than this. So there is no, for here, no path length difference. For straight across. But once we go up and down, the path length difference changes. And the total phase changes because the path length is factored into the total phase. So as the path length difference increases, the total phase, the difference between the two phases increases. So we see that this is zero. The total phase here is zero. The first one, it'll be 2, and then it'll increase. Okay. So how do we get to this total phase? This is something that kind of when I was first learning this, it kind of like, I was confused how we got from here to here. But the thing to keep in mind is that this is the equation for a wave. So k equals 2 pi over lambda, right? And this omega times t is based on time, right? Is based on the period. So since they're coming from the same source, this is negligent. This is negligible. We don't need to worry about this. The only difference is the phase constant. And so because the phase constant is coming from the same source, this will ultimately be zero. This phase constant will be zero. So what we really have is the difference between the total phase from this one and minus this one. And once we do some factoring, so we can do 2 pi times r over L plus the phase constant, minus, and then this would be total phase 1 minus 2 pi r. So I should just do the path length difference over lambda plus the phase constant. And when we factor them out, we will see that we get basically the same thing. We get this equation because phase two, or phase two minus phase one. I should say this is phase two. So yeah, and we can talk way more in depth. This is kind of like the general information you need for the worksheet I just posted. So hopefully this helps, and we can talk more in depth during my Zoom sessions, which are Tuesday and Thursday from 2 to 3. So, and thank you guys.